Let's approach this question very confidently. Okay, so a 50 feet ladder is placed against a large building. The base of the ladder is resting on an oil spill and it slips at a rate of 3 feet per minute. Find the rate of change of the height of the top of the ladder above the ground at the instant when the base of the ladder is 30 feet from the base of the building. Okay, so the situation we have in this case is let's take this to be our building. Okay, and then we are told a 50 feet ladder. So we have a 50 feet ladder leaning against the wall. Okay, and then we are told the base of the ladder is resting on an oil spill. So let this be an oil spill. Okay, and then this ladder is, and it slips, so there's slippery there because of the oil. So it's like what is happening is, so as it slips, you know that this part will be going down. What you know is as it slips, it will be reducing and then it will be moving this way. So what will basically be happening in action is, so as it slips there, it will become longer like that, and then so it's like the base is getting longer and longer. So as it gets there, so one thing that we can notice, as this ladder slips on the surface there, its length will not change. It will remain 50 feet no matter the position. Okay, so let me just indicate the information we have. So we have 50 feet, that's the ladder, and then the base of the ladder is resting on an oil spill and it slips at the rate of, so the rate at which this is the slippery part is at the rate of 3 feet per minute. So in short, we can think of that to be an increase in the base. Okay, let's take our base to be the x, and then the the height of a building to be y. Okay, so as the ladder slips on the base is in short, x is increasing at that same rate that we told the ladder is slipping. And then find the rate of the change of the height. So find the rate of the change of the height of the top of the ladder. Find the rate of change of the height of the top of the ladder above the ground at the instant when the base is 30 feet. So we are told now at the point where the value of x, which is like representing the base, is 30 feet, find the rate at which the height will be increasing or be reducing actually. Find the rate of change of the height of the top of the ladder. So the height in this case is y, and of course we expect that it's decreasing, right? Okay, so expect to find a negative rate of change of y. So what they want us to find is change in y, of course in respect to time, because we're talking about the rate. So the 3 feet per minute, which is the rate at which the ladder is slipping on the oil spill, indicates the rate of change of the x. So that is the rate of change of x. Okay, so we have dx, want to find dy dt, and then we've also been given the value of x at a certain point. So at that point where x is equal to 30 feet, that's why they want us to find the rate at which we expect the y to be changing. So we can find the value of y at that initial point, since we know that no matter the position of the ladder, even as it goes down, its length will not change. Even if it's there, the length will still be the same. So meaning that we have a triangle where we're able to find the value of y at the instant where the basis of the ladder is 30 feet. So by Pythagoras theorem, we know that the ladder itself is the hypotenuse, so it's supposed to be equal to the summation of the base, which is at 30. Now at that instant, instantaneously, the y value is expected to be what? So we can try to simplify that. So 50 squared minus 30 squared is equal to y squared. And then of course, if we simplify that, we have to find the square root of both sides. So the y value that I'm getting is 40. So we have the y value as well. Okay. So now our goal is to find the rate of change of y, which is like representing the height of the building where the ladder is leaning against. Okay. So if we try to write the equation again, we'll take the hypotenuse, which is the length of the ladder, to be, let's say, z. So we'll say x squared plus y squared, which is representing the height and also the base, should be equal to 50 squared, which we know that the reason why I'm just putting 50 squared is because the length of the ladder will not change, but these other values, x and y, will be changing. The height and the base will be changing as this ladder slips. Okay, so our goal is to find the change of y. So what can we do there? We can try to differentiate everything in respect to t. So for the first part, derivative of x will be 2x. Now we are differentiating x in respect to t. And then for the other part, it will be 2y. We're differentiating it in respect to t as well. So you can see dy dt is already appearing. And then here it will always be a constant. So the derivative of a constant is a 0 multiplied by the height there. So you can say dz dt. So it doesn't matter anyway, it will still be a 0 on the right. So this part we have a 0 because the length of the ladder will still be the same, because the derivative of a constant is always 0. Okay, so at that point, remember our goal is to find dy dt, which is the rate of change of the height. So we have 2y dy dt, and then the other part can go the other side. This part can go the other side. So it will become negative 2x, and then dx dt. Okay, so we can divide both sides by what? We can divide both sides by the 2y there. 2y. So we can have 2y. Okay. So on the right hand side, on the left hand side, it will disappear. So what remains is as follows. The equation that is standing out, I think I can remove this part as well. The equation remaining is dy dt being equal to, so first of all we have a product of okay, I think this can divide, the 2 and the 2 can cancel out, so that we remain with negative x, and then negative x what? Negative x multiplied by the dx dt, and then after this computation we are now dividing by the y that is coming from the other side, divided by the y, okay, which is on the bottom there, and then we can substitute. So do we have the value of x at that initial point? So negative, the value of x at that initial point, we are told the base was 30 feet, so 30, and then dx dt, which is like the rate of change of the base, is 3 feet, and then divided by y, which at that initial point was determined to be 40. So negative 30 multiplied by 3 is negative 90, divided by 40, or negative 40, or positive 40. So here the answer that we're getting is negative 2.25. So that's the rate of change of the height. So of course we had feet there, so feet per minute. So that's basically, I believe these 6 questions have given you an idea, at least an understanding, a basic introduction to on how you can approach related rates, applying differential calculus with the use of implicit differentiation, and also understanding the rates.